Hello everyone. In this video, we will learn how to find eigenvalues of a given square matrix. Well, let me quickly recall what was an eigenvalue. Lambda is an eigenvalue, a number lambda is an eigenvalue of square matrix A if a v is equal to lambda v for some vector v which is not 0. As we saw, if I know eigenvalue, I can do some work and find eigenvector. And if we know eigenvector, we can find eigenvalue. But now the question is that I have to start from somewhere. How can I find eigenvalue first? And then go ahead and find eigenvector. Here is the theory. There's a theory behind this, and you will see how we develop that. When you look at that AV equals to lambda v, and you open it and write it as equations. Well, let me just do it for 2 by 2 matrix. So this is a11, a12, a21, a22. Xy equals to lambda x, lambda y. Yes. And then I write this one as equation and take x and y here to the left hand side. So what I will get will be a11 minus lambda x plus a12y equals to 0, and a22x plus a21 times x, a22 minus lambda times y equal to 0. And while if lambda is an eigenvalue, then the system has there is a non-zero solution there. Solution for the system. But if you look at that system, it is nothing but the coefficient of that system is a11 minus lambda, a12, a21, a22 minus lambda. Well, this is like we have the matrix A, which was a11, a12, minus this guy, which is lambda, lambda on the main diagonal, everything else is 0. Other way of writing this is A minus lambda 1, 0, 0, 1. This guy is a famous matrix. For any m by n matrix which have 1s on the main diagonal, everything else is 0, we call it the identity matrix. And basically what we see is this. The coefficient matrix of this guy is a minus lambda I. And so a minus lambda I times v is going to be 0 for some non-zero matrix, vector v. This means simply that a minus lambda I maps a non-zero vector to origin. Yes, this is the origin. And well, that is equivalent actually to say that a minus lambda I, or the linear vector field defined by a minus lambda I, is not invertible. You may say, why are you going all these steps? Because this is where we have the starting point of a big, nice theory. a matrix defines not invertible linear vector field if and only if the determinant of that guy is equal to 0. This is where you can start working. So if someone gives you a matrix, what you do, you find A minus lambda I, or in other words, you write A, on the main diagonal you put minus lambda, minus lambda, minus lambda, and then find determinant. You will find a polynomial in lambda. So this is a note, I will put note. Determinant of A minus lambda I is a polynomial in lambda. And, well, we are trying to find what are the roots of that polynomial. And eigenvalues of A are roots of that polynomial. This means what? This means that to find, if someone gives you a matrix, you just go find A minus lambda, determinant of that, that's a polynomial. Find all the roots. The roots are the eigenvalues of that matrix. And since that polynomial is important polynomial for us, we have a name for that. The polynomial det of A minus lambda I is called the characteristic polynomial of A. So finding eigenvalues, you find characteristic polynomial, set it equal to 0 and solve it. Let's see this in some examples. Find the characteristic polynomial. Remember, what is characteristic polynomial? Determinant of A minus lambda I. So in this case, this means that determinant of A, which is 1, 4, 5, 2, minus lambda I is this. Or simply what you do, you write the matrix and add to the, subtract the diagonal entries. The diagonal entries are these guys. My lambda, subtract lambda from the diagonal matrices. This is 1 minus lambda, 2 minus lambda, minus 4 times 5. Okay, so let's just solve this. This is lambda squared minus 3 lambda plus 2 minus 20. And the characteristic polynomial is here now. We found the characteristic polynomial. So that is what we have, the characteristic polynomial. Now the eigenvalues is just simply set it equal to 0, eigenvalues. Set it equal to 0, so lambda squared minus 3 lambda minus 18 is equal to 0. Well, actually, I can't decompose this polynomial. I'm looking for two numbers add up to negative 3. When you multiply, you get negative 18. This is negative 6 and plus 3. And then from there, either lambda is 6 or lambda is negative 3. So A has two eigenvalues, lambda 6 and lambda equal to negative 3. This is where we can start now. So now you can find eigenvalues and then go from there and find eigenvectors of each one. Let's do this other one. This is the second example. Characteristic polynomial, determinant of the, write the matrix minus lambda I. Lambda I means that subtract lambda from the diagonal entries. And here I have 3 by 3 matrix, so I will expand on the first one. This guy is the first, so minus 1 minus lambda, minus 1 minus lambda times determinant of 3 minus lambda 2 4 1 minus lambda plus the second entry. The second entry, you see that I'm going to deal with something which is going to be multiplied by 0. So that means that, actually this must be minus 0 times determinant of something, and the third entry of the first row is 0 as well. So I will be good there. So that means that my polynomial, okay, so we're getting it together, 3 minus lambda, 1 minus lambda minus 8. This is a minus 1 minus lambda, lambda squared minus 4 lambda, and plus 3 minus 8. And that will give me negative 1 minus lambda. Better to not expand because, when you have decomposition of your polynomial, you can solve it. So polynomial is this. I actually can go ahead and decompose the quadratic part again. So two numbers adding up to negative 4 multiplied to negative 5. So this is negative 5 plus 1. Now set this one equal to 0. Eigenvalues. Minus 1 minus lambda, lambda plus 1, lambda minus 5. This is equal to 0. So it's minus 1 minus lambda equal to 0. Lambda plus 1 is equal to 0. Lambda minus 5 is equal to 0. So these two guys gives me only one eigenvalue, one value, and this is another one, yeah? So that means that we have 2a has 2 eigenvalues, lambda negative 1